All right, let's talk about the common ion effect. It sounds kind of technical, right? But it's this amazing, secret balancing act that's happening all around us, and even inside us, from our own bodies to giant factories.
Okay, ever wonder about this? You down an acidic soda, right? And nothing really happens. Your blood's pH stays perfectly stable. How? I mean, really, what's stopping it from just going completely haywire?
Well, it's not magic, that's for sure. It's this incredible, invisible chemical balancing act. And trust me, once you see how it works, you're going to see its fingerprint everywhere, from your own biology to the stuff you use every single day. So let's dive in. To really get how our blood performs this little miracle, we've got to understand why this kind of balance is, well, absolutely crucial for life.
All right, so meet the hero of our story, the buffer solution. Think of it like a chemical bodyguard or a shock absorber. Its whole job is to take a hit. You throw a little acid at it, a little base, and it just stands there, holding the line, making sure the pH barely budges. And yep, you guessed it, our blood is one of the best buffer solutions out there.
Okay, so what's the secret sauce? What makes these buffers tick? Well, it all boils down to one key chemical idea. The name is simple, but its power is, well, it's a real game changer.
And that is the common ion effect. Basically, it's what happens when you dump an extra dose of an ion into a system that already has that same exact ion as part of its chemical balance. This one little move can totally shift the entire equilibrium. Let's see how that plays out.
Okay, picture this. You've got a weak acid, something like the acetic acid you find in vinegar, just sitting in water. It's in this delicate equilibrium, right? Only a tiny, tiny fraction of its molecules actually split up into ions. Most of them are just hanging out, whole and intact. Now watch this. This is the key move. We add a salt, let's say sodium acetate. It dissolves and whoosh, releases a flood of acetate ions into the water. And that acetate ion, that's our common ion. Why? Because it was already there from the weak acid. So now the system is just swamped with it, totally overloaded.
So, we've just totally stressed out this poor chemical system by dumping in all these extra ions. What does it do? How does it fight back? Well, chemistry has this amazing, built-in rule for exactly this kind of situation. It's got a fancy name, Le Chatelier's principle. But the idea is super simple. If you have a system that's in balance and you mess with it, it will literally shift itself to undo what you just did. It's chemistry's natural instinct to find balance again.
The seesaw is the perfect way to think about this. You know, you put too much weight, or in our case, product, on one side, the seesaw tilts back the other way towards the reactants to balance things out. It's this beautiful, constant, self-correcting dance.
Okay, let's connect the dots and see the buffer in action. So, we've got our solution, armed with both the weak acid and this huge stockpile of its common ion. Now, in comes the enemy, an outside acid, H+ ions trying to mess up the pH. But that big reserve of common ions, it acts like a sponge. It just soaks up those new acid ions, reacting with them to make more of the harmless weak acid. And just like that, the threat is neutralized. The pH, it barely even twitches.
And this is way bigger than just a cool trick our blood does. The common ion effect is a seriously powerful tool. We're talking about something used everywhere, from tiny labs to absolutely massive industrial plants. Yeah, this effect is at the heart of so many things. Purifying chemicals? Check. Making the products you use every day? Check. Cleaning up our water supply? You bet. The list just goes on and on. Take salt purification, for instance. You've got this messy, brine solution, you can just flood it with the common chloride ion, and boom, it forces the pure table salt to crystallize and literally fall right out of the water. We use the exact same idea to get solid soap out of a goopy mixture or to soften hard water by making all those nasty minerals clump together and drop out as solids.
And here's a huge one, the solvay process. This is the industrial scale method for making baking soda. Yep, the stuff in your kitchen. The whole thing hinges on using the common ion effect to perfectly control when the sodium bicarbonate becomes a solid so it can be easily collected from the liquid.
Yeah, this quote really nails it. By cleverly adding a common ion, you can basically tell a specific chemical, okay, your time in this liquid is up. Turn into a solid now. It gives chemists an amazing level of control, like having a remote control for precipitation.
And that control is absolutely vital when you're playing chemical detective. I mean, look at this flow chart. It's like a step-by-step guide for forensics.
By adding specific common ions one after another, chemists can force different metal ions to drop out of a solution one group at a time. It's how they can take a mystery goo and figure out exactly what's inside.
So the big point here is, this is not just some dusty textbook theory. No way. This is a hands-on, practical tool for bending the chemical world to our will. And the numbers, they really show you the power we're talking about. Let's go back to our buffer example. By mixing acetic acid with its common ion, we can create a solution and lock in its pH at a super specific, super stable value. Right here, it's 5.05.
Now check this out. This is where it gets really dramatic. On its own, that weak acid is pretty acidic, with a pH of 2.78. But the moment we add that common ion and create the buffer, we totally shift the balance, and the pH jumps all the way up to 5.05. This chart says it all, doesn't it? It shows you just how powerful this effect is. It's the difference between a simple acidic solution and a rock-solid, pH-stabilizing machine.
So the common ion effect, it's just a perfect example of one of these invisible rules that's quietly running the show, you know? From the chemistry inside our own cells to the biggest factories on Earth. It really makes you stop and think, right? What other hidden principles are out there, shaping our entire world, just waiting for us to notice them?